Good evening. So very good evening to all of you. How are you guys? It's very long to see you, you know. So how everybody is getting with physics? I hope every one of you are doing good, na? Okay. So very quickly, please let me know if the screen is visible to you and I'm audible to you. Arey, I'm very fine here. Thank you for asking. So make sure the screen is visible to you and I'm audible to you. Give me the thumbs up or whatever reaction you can give. Okay. So I welcome you all in this series of lecture on gravitation. This should be our last lecture, I think. And previously we have covered about the relation between gravitational potential and the gravitational field intensity. Okay. I hope you guys have remembered it. In today's session, we are going to see that what are the gravitational potential at a point possessed by different shapes of bodies. Okay, different bodies, like we have seen in the gravitational field intensity. We have also seen the gravitational field intensity due to different bodies. So same we are going to do in this also. We are going to see uh, what is the effect of the gravitational potential when a body shape is changed. Okay. So without wasting so much time, let's get started with the lecture. That's lecture number 10. So the topic that today we are going to cover is the gravitational potential due to different bodies. Like we change the body, we will take point mass firstly, then we will move on the uniform thin spherical shell, then uniform solid sphere, and then finally the ring. Okay, that we are going to see that how the potential affect by the shape of any body. Okay. Actually, the potential, the gravitational field intensity, all of these phenomena changing because of the shape of any body. It is changing because of the mass distribution of the bodies. In uniform solid sphere, you have a different kind of mass distribution. In uniform spherical shell, thin spherical shell, or a hollow sphere, you have another kind of mass distribution. In you also, in a baby and in a young man, there is a different kind of mass distribution, no? So that is why the potential of any kind of body will vary. It is not varying, although I'm not saying that the shape factor will not come into contrast. Yeah, it will come, but the main reason, the bigger reason is that the mass distribution of them. Okay. So how the mass is distributed along a length, along a volume, or along a area, it will decide the final values of these gravitational intensities and the potentials. Okay. So it is not the shape, it is it is also the shape, but the major part is mass distribution, how the mass is distributed. Okay na? So keep remember. Then we are going to see Earth satellites. Although we have covered the satellite energy, satellite velocity, the orbital velocity, the time period of a satellite, and the energy of total energy of a satellite, we have also covered it. Okay na? So today we are going to see what kind of different satellite we can use around the Earth for the telecommunication purpose, for broadcasting, for any other of these types of services. and what is the weightlessness. Okay, so let me just start. So firstly, I will tell you the gravitational potential due to point mass. Okay. Before that, what we are going to do, we are going to do a recall, quick recall. Since it's been a very long time for you guys to attend the session, and I hope that in that time period from I think from Saturday to today, there will be no class for Monday and Tuesday, na? So I hope that every one of you have revised the concept and do a proper numericals and proper studying hour you have dedicated to it. Okay, JNV. So what is your actual name, JNV? Haveri is showing to me. Okay. So it's very good to know that some of you, I think every one of you are focused enough or determined enough to achieve that goal. Okay, achieve that aim. Now, what we have done in the previous class, we have done with the Kepler's law, and revision we have done the Kepler's law and the gravitational potential we have studied. I have told you that gravitational potential, this gravitational potential is nothing but the work done per unit mass to bringing a point mass from infinity to a certain point. Okay, na? That is the that is called as gravitational potential. So from the definition, you can see that the gravitational potential, actually the change of gravitational potential is defined. Okay. Because if in your class, there are two students. So one of the student has get had different potential, another has different potential. So you cannot tell that what the exact potential that a student can have. Okay. Although you can compare it, like if there is two student at Ramu and Shamu, so you can say that Ramu is much better than Shamu in that particular field, in science, in mathematics, and Shamu is more capable of doing things in creative field like arts and all. So there are different kind of perspective, different kind of respect that you can have. With respect, we will use that term, no? So different types of perspective you can have. Okay. Now, so the actual potential you can, only the difference of potential you will know. Okay. But if you will know that where is the potential is zero. Like, I'm not saying it to any person with respect to all the students. I'm saying that because I have to use this example. Like one of the student in your class is very poor in learning English. Like is the reading skills and especially in English is zero for it. Okay? Zero for him. He can't. He's not able to read a single word in English. So you can say that at that particular field, from the point of view of learning, we are saying that the potential of that particular student in reading English is zero. है ना? And then you can compare that all the other student capability or possibility. ठीक है ना? ठीक है? So I'm not suggesting you that you will name any of your friend with the potential zero. No, don't do that. Okay? Because if anyone has a potential zero in a particular field, he definitely will be a master of in another field in which you have no knowledge. So try to respect each and everyone. है ना? So delta V is nothing but potential energy per unit mass. Why the potential energy? Because the potential energy. Okay, Suhana, you are with me now? You agree with me? That is why you are writing yes, sir. It's very good. And thank you so much. So the potential energy is the negative of work done by conservative force. Okay. Like I will tell you that if this is the point mass na, and it is infinite, it is at infinity, and here is a point at point A, and you have to bring that point mass to this point, at this point. So you have to put the work. Okay, you have to put some work in it, because this point A is another gravitational field. This is a gravitational field created by another mass particle. So you have to bring that mass from infinity to this point in a gravitational field by another mass particle. Okay. So what is happening? This gravitational field is constantly applying a force in that. Okay. But one of the condition, if we will free this mass particle, what will happen? This mass particle, in the effect of this force, like this F force, it will experience an acceleration. So you are not able, because when this particle will accelerate, there is a term kinetic energy will come into contrast, and it will disturb the potential energy phenomenon. Okay. Because potential energy you can only measure in the case when there is a particular fixed position of that. You know? So the potential energy come into contrast, and it will disturb the analysis that we are doing, because we are only interested in the potential energy. So what we will do, we will have first situation, this acceleration 0. This is the condition that we need. So there is a force acting already. So what we have to do, we have to apply a opposite force of it. Just equal, just a little greater and equal to this force. Okay, so that this particular mass particle will travel from infinity to this point very slowly and not accelerating with the negligible speed. Negligible, negligible, negligible speed. So the kinetic energy will be 0. Okay. Now you will see that potential energy I have defined as negative of work done by conservative force. Why? Work is done by this force, because this is the force we are holding. This is the force we have applied, but we do not know the value of this force. But we can calculate the value of this conservative force because of the Newton laws of gravitation, in which we have been told that the force applied by a particle on another particle is gm1 m2 by r square. Got it? But this force is acting opposite. Sorry, the applied force is exactly equals to this force. Okay. So we can replace, because this value we know this value. So we can replace this. But if you will see that the work done by F1 is equals to F1 dot dr, or F1 dot r. R is the, let's say R is the displacement from an infinity to A. But R is in this direction and force applied in opposite direction. So there is an angle of 180 degree in between them. So this will be minus of FR. And got it? Because this will open as FR cos 180, cos 180 is minus 1. So it will be minus FR. Now you can replace this F1 with FC, because F1 we do not know. We know the value of conservative force. So it is FC. That is why the minus will appear here in the work done, in the potential energy. Okay? Got it? And that is why we are writing this potential also in terms of this gravitational potential energy. So this potential is nothing but the gravitational potential energy per unit mass. You can how much potential it has. Got it? And gravitational potential is energy is nothing but the negative of work done by conservative force divided by mass. So this will be used as the gravitational potential. Okay. And another thing that we have learned is the relation between gravitational potential energy, sorry, gravitational potential and gravitational field intensity. That relation is dV is equals to minus of E vector dot dr vector. And I have told you that by this default, this expression will lead you a conclusion that if you will move in the direction of, if you will move in the direction of gravitational potential, so what will you have? If you will move in the direction of the gravitational field, that means you are going in decreasing potential. Because if this is the gravitational field, let's say, and you are moving from this point A to this point B in the direction of gravitational field. So from here you will say if this displacement is R, so you can say that the change in potential is minus of E dot R, है ना? And it will become minus ER, and this is V2 minus, or you can say it is the gravitational potential difference between B to A. So it will be VB minus VA, okay, which is negative, which means that VB minus VA is negative, yani less than 0. So VB is less than VA, which means in the moving direction, in the direction of gravitational field, the potential will decrease. Okay, got it? So this is we have done. Now a gravitational potential due to point mass. What we are going to do, we are using the relation between gravitational field intensity and the gravitational potential. And by that expression, because we know the expression of gravitational field intensity due to point mass. Okay, we have already covered it. So what we are going to use, we are going to use the relation between potential and intensity and put the expression of intensity for that particular body. And here it is point mass. So for point mass, we are going to use that, and we will have the expression in our hand. Now, firstly, I will write the gravitational field intensity for point mass. Okay. So for point mass, it is E vector is equals to Gm over R square into R cap minus, है ना? Minus mean it is attractive in nature. Okay. So what we are going to use here, we are going to use the relation between gravitational field intensity and gravitational field potential. Okay. So suppose there is a point mass here. This is point mass, and this is the field intensity I. Okay. And this is the displacement R. Got it? So now in the second step, the relationship, now the relation between gravitational field intensity and gravitational potential. We are going to use that, and it is nothing but dV is equals to minus of E vector dot dr vector. Okay, got it? Now this dv is equals to minus, put the value of e, and e is nothing but minus gm over r square dot r cap, minus gm over r square dot r cap. ठीक है, dot dot dr vector. Now from the knowledge of vector you have studied, you can say that any vector a, any vector a can be represented by its magnitude multiplied with its unit vector. Na? Got it? So dr vector we are also going to use in this form. So you can also write this dr vector as the magnitude as dr dot r cap. Okay, got it? So dv is equals to minus of gm over r square r cap dot dr into r cap. Now dr is constant, you can take it out. So dv you have as minus of gm over r square dr r cap dot r cap. And you know that if unit vector, if unit vector has a dot product with itself, then it will give you 1. Okay? So dv is equals to minus of gm over r square dr. Okay? Got it? From where to where we have to integrate it? So the potential dv is equals to minus of gm over r square dr. Now we have to integrate it, and we have to integrate it from infinity to r, है ना? So from infinity to r we have to integrate it. At infinity, what is the value of potential? So we would assume it is 0, and at r the value of potential will be v. So v minus 0 is v is equals to minus of gm is constant, and integration of 1 upon r square will give you minus, integration of 1 upon r square will give you what? It will give you 1 upon r or minus r. Tell me in the comment box. Will it be minus 1 or plus 1? Tell me. Yeah, definitely it will be minus 1. Very good, Aisha. So the gravitational potential, you will see that here in the dot product, this dr vector, that is the displacement vector, and this intensity vector are in opposite direction. ठीक है ना? Got it? Because of that force that we have applied. So here this product will lead you minus 1. So that is why this dv is nothing but the positive gm over r square dot dr, and it will be positive. So finally what you will have, or it will give you v is equals to minus of gm over r, because 1 upon infinity will equals to 0. ठीक है? Got it? So this is the expression for point mass. Or one thing that we have uh, do it mistakenly here. Just a second, I will tell you. You guys are not paying attention to this. This E is already in negative, and this is minus E here. So this minus minus will give you plus, na? There is no need to be this definition. Okay, got it? So if anyone have any kind of doubt in this expression, you can ask. Then we will move forward. Okay. So make sure this expression is clear to you, how to derive it. Huh? Each and every one of you. Okay. This minus sign here is indicating that the work done by the gravitational field is positive. So work done by gravitational field is positive here. And it implies that this negative sign also implies that the potential energy decreases. ठीक है, पूरे सिस्टम की जो पोटेंशियल एनर्जी है, it will decrease. And why it is so? Because you are bringing that particle from infinity to a particular point. From infinity the potential is zero, the potential energy is zero, which is a very good condition for the stable equilibrium. Because as much as low value of potential energy you will have, it will good for you, and you are taking back to this. ठीक है ना? So the potential energy is also decreasing because you are putting effort in that to bringing that particle from infinity to this. So all these efforts are being stored in terms of energy, and that energy is potential energy. Thank you, Aisha. Now the uniform thin spherical shell. Uniform thin spherical shell is nothing but a uniform hollow sphere. You can also tell it. Just a second. It is a uniform hollow sphere. Okay. Now the same thing we are going to use. Firstly, tell me that if I have a point outside the sphere, whether it is point mass, sorry, whether it is a solid sphere or hollow sphere, will the expression for the gravitational field intensity be same as the expression for point mass, or it will be different? Just let me know, each and every one of you. Like if I take a point which is outside the uniform hollow sphere or solid sphere, so will the solid sphere or hollow sphere I can consider a point mass or not? So the first thing we are going to learn here, the point is outside. Okay. So none of you have told me, but I will tell you according to the shell theorem that I have discussed in the gravitation. According to shell theorem, we can consider if the point lies outside the uniform bodies, you can consider that body to be a point mass and all the mass situated at its center of mass. Okay, or centroid of that body. Okay. So for point outside, the gravitational field intensity formula is same. E vector is equals to minus gm over r square. This is point P, and this distance is smaller. So the potential, we have derived it earlier in the previous slide. It will not change. It will be minus gm over r for point outside. For second point at surface. So what will happen to the surface? This point is coming at this point. So this r will reduces to, r will become capital R. So you can put it v is equals to v at surface. You can represent vs. It will be minus gm over capital R. Now, point inside the sphere, inside the sphere. Now, you know that the point inside the sphere means point is here somehow. So how the R changes? This R, okay, the you want the relationship now. I have told you that R will varies as hyperbolically. Okay, at R it will be maximum. Okay, I'm drawing this graph for the first quadrant. I'm considering this to be positive, but if you will consider it to be negative, the graph will be in the fourth quadrant. Okay, I will tell you. Let me discuss it. This point. So point is inside the sphere. Point is somehow here or here or here. Okay. So we know that for hollow sphere we have learned that if any point lies inside the sphere, the field intensity will be zero at that point. Okay. So if we use this expression, which is dV is equals to minus E dot dr. Okay. And if you integrate it, got it? And this is zero, which means something that is dv is equals to 0 because this E is 0 inside. है ना? If this dv is 0 means the difference between the potential inside any point, between the point lies inside the sphere is constant. Okay? So there will be no change in the potential inside the sphere. But what is the value? The value will hold because the minimum value, the maximum value, sorry, at this point P, you have a value if the distance is smaller. So we know that this V is also varying as 1 by R. So as R increases, V will decrease. Up to how much extent it will decrease? It will decrease to surface. Okay? Because further, there is no scope of decreasing. Further, you will know that inside any point, the potential is 0. Sorry, the potential difference is 0, which means the potential is constant. Okay? So the minimum value that you have at the surface, further it will not decrease, remain constant. So what is the value of potential at inside? Tell me. If this is the sphere, this is point is in the surface and this is just adjacent to it. This point is just adjacent to it. Okay. We know that inside the sphere, potential will not change. V is equals to constant. Okay. It is not changing. And from here point P to this point, it is changing. Okay. And it has a minimum value at this point at surface. Vs. So what is the value of potential at inside at this point, which is just adjacent to it? Tell me, will it be the value of potential same as the value of potential at surface or it will be different? Any one of you? Any guesses? Serena, Rajesh, Ankita, Aisha? Any guesses? If the potential is constant inside any point of the sphere, and at surface it has the minimum value, it means that further it will not decrease. So what is the value of potential at point inside the sphere? Tell me. Okay, so I will tell you that potential inside the sphere will be equals to potential at surface. ठीक है? So it will be treated as this, and this must you have remembered that potential difference between any 2 points inside the sphere, that will be a hollow sphere, will be 0. ठीक है? Got it? And if you are interested in graph, like Aisha has asked, so this graph will look like this. This is V and this is R. Since this is a negative value, so at surface, from inside, if you will tell, from R is equals to 0 to capital R, it will a constant value. It will be a constant value, which is minus GM over R, capital R. And further, it will decrease in a hyperbolic manner. This is the graph for it. Okay? Got it? Anyone, any kind of doubt? You can ask. Now, for uniform solid sphere. So in uniform solid sphere, we have to discuss two cases. First is outside and another one is inside. Okay? Now, if you will ask me the inside value, sorry, the outside value, we know that if it is a solid sphere, and there is a point P here outside at a distance R from the center, so we can treat it as a point mass. So this will convert as point mass, and this point is exactly our distance from this point mass. And this point mass has a mass of total solid sphere mass. Okay. So for inside, for outside, we are not so much. This is not so much disturbing. So you can write the expression for outside. We will have as V is equals to minus GM over small r. And at surface, at R is equals to capital R, V at surface, we have GM over capital R, minus GM over capital R. Okay. But we know that what we know? We know that the inside the solid sphere, the gravitational field intensity is not 0. We have already derived the expression of that. Okay. And that expression was, for inside I'm talking about, for like we are dealing with a danger expression, so we have used a danger color. For inside, the gravitational field intensity E is equals to what is the value of that? It is Gm small r divided by r cube minus, and it is r cap. Got it? Remember that inside the solid sphere, the gravitational field intensity varies linearly with r. है ना? So apply the relation now. So the relation is dv is equals to minus e dot dr. Okay. So dv here is nothing but, put the value of e, it will become plus gm small r divided by r cube, r cap. Dr vector again you will write as dr r cap. R cap and r cap will become 1. So dv here you have gmr over r cube into d. Okay. So now the interesting part is the limit. What is the limit you will take? It is G capital M small r. What is the limit you will take? Are you calculating the potential from infinity to that point? No. From infinity to that surface, we have already calculated this minus gm over r. It is the potential outside. The infinity is outside. है ना? You are talking about the inside material, inside point. So inside, what should be the possible limit from where one thing can expand? Batao. Any one of you, please responsive na. That is why your brain will open, and you will get to know. Yeah, that is why we are using this limit. I will tell you immediately if you want, but I want you guys to be engaged. Yeah, and that is what really help you out. Okay, na? That will build your logic inside your brain. And for understanding physics, you need a logic. Without logic, there is no physics. Okay? Physics is logic. Any one of you are able to tell me the limit? Batao. Okay, I will tell you two options. So you just have to pick one. Okay. Option one is from infinity to small r, and second infinity to capital R, and third small r to capital R. So please tell me, what is your option? What limit you will choose? Will it be 1, 2 or 3? Now it is simple na, for you to answer. Answer it. Then I will proceed if you will answer. Ankita. Aisha. CNV Haveri. Okay, two guys have answered only. What about another? What about others? Rajesh, Serena, Bharat. What about you guys? It means and only two guys are responsive. Only two guys are attending the session. Okay, Serena has chosen two. Okay. Okay. And what about you, Bharat? Please respond. Let me see now if you're guys attending the session or you just opened the Zoom link and put it on mute and all. Okay, Mallinatha. So only 3 students have answered. Okay, na? And it is not good thing. Okay, Mallinath, Purushriva, Shankar. So it's also 2. So the balance is there. Na? 2, 3 of you guys are saying that it is 3. And 2 of you are guys saying that it is 2. Okay. Now let me tell you. This is a solid sphere. This is center of it, and this is the radius. We are talking about potential inside of it. This thing will clearly set you up the limit. You don't need to focus on another thing. But the point we have to capture inside. From where we can capture this point? We can capture this point here. We can take this point here, here, here. Up to this point, up to surface, we can take it from the center. And this can vary from here to here, here to here. But the minimum limit for it to be at center. Okay. And maximum it to be at surface. But suppose suppose this is capital R. Suppose that we have taken this point here. This is point P from where we have to find potential. And this is the radius of that sphere in which P is situated. Okay. So what should be the possible limit of that? It should be from small r to be capital R. This. So this radius can vary from small r to a finite value to the radius of the sphere itself. Okay. Got it? So the correct option is option 3. Okay. And very good. You have answered it. You have been responsive. It's very good. Okay. Those who are correct with their option, congratulations. And those who are not, so a very big congratulations to you guys. And why it is so? Because you have learned a new thing. Okay. Yeah. Thank you. Got it? So limit should be from small r to be the capital R. Got it? Or you can say from capital R to small r. At capital R, you will have a potential at Vs, and small r you have to know it. So it is V. You can say that V minus Vs is equals to. Now Gm and R cube are constant. So only R is there. It will become R square. So you can take Gm and R cube as common. So it will become R square by 2. है ना? Integration of x dx will become x square by 2. And limits are capital R to small r. Now V minus Vs is equals to Gm over R cube. And this R square will become R square by 2 minus capital R square by 2. Okay. Now, V is equals to, we have taken Vs from left hand side to right hand side. V minus Vs, Gm over R cube, R square by 2 minus capital R square by 2. Now, V is equals to Vs plus Gm over R cube, R square by 2 minus capital R square by 2. Okay. This Vs has a value of minus Gm over capital R. Minus Gm over capital R plus Gm over capital R cube into, you can say that R square minus capital R square by 2. So if you take the common minus Gm over R, if you will take this thing as common, which is minus Gm over 2R cube, then the thing you will have inside is 3R square minus small r square. So this is the final expression you will have inside the sphere. Okay. The graph of it will be the graph of it will be look like this. This is potential, this is R. Okay. For inside, let me just redraw it. For inside, the variation up to the surface, it will have the value Vs. This is Vs, and after that it will decrease in a different manner. So this variation, and it is not a sharp point here, yeah, This is not a sharp point. So it is a continuous point. This varies from here to here. Okay. This variation is, if you put R is equals to 0, then the potential that you will have here. है ना? So this variation is parabolic. But this variation after it crosses this point, crosses this surface, the variation will become hyperbolic. Hyperbolic. ठीक है ना? So this thing you have to keep in your mind. And this value is nothing but the value at r is equals to 0. So if you put r is equals to 0, this will become minus gm over minus 3gm over 2 capital R. ठीक है? Got it? Now, for the uniform ring, so for uniform ring, it will be a homework for you. Okay? You have know the expression for intensity. I will write it here. The intensity is nothing but gmx divided by capital R square plus x square raised to the power 3 by 2. है ना? So this expression you will have I cap, because you have measured this intensity in x direction. So intensity, sorry, I will write it as E. So intensity you will have. Now you have to calculate the potential. How you will use the potential? You will use the relation between potential and intensity, and then find the general expression for gravitational potential. So this will be a homework for you guys. ठीक है ना? Try to do this, or if you are not able to do this, I will discuss this in next lecture. ठीक है? And the next lecture will be the last lecture of this session, of this topic, the gravitation. So if you till now, if you have any kind of doubt, you can ask, or otherwise the lecture is been over. Thank you so much for being attentive. ठीक है? Take care. Bye bye.